Hi, this is a video to explain to you that there is more than one way to solve a system of equations. One of those ways is using inverse matrices. We've already studied a lot of algebraic ways: elimination, substitution, Gaussian elimination, Gauss-Jordan elimination, using RREF or reduced row echelon form. Again, lots of great ways to solve. You can also use what are called inverse matrices to solve a system. The first thing we need to understand is what is an inverse matrix. Now there are kind of two ways to find them. If it is just a 2 by 2 matrix, which kind of goes to show us something, basically what we can do is take a 2 by 2 matrix, so such as the one up top here, matrix A is the matrix A, B, C, D. To find its inverse, and you'll notice in the middle of the screen there, we've got A inverse, right in the middle of the screen, right here. That little 1 or -1 in the exponent is the symbol for inverse. Again, that's not a reciprocal. It's not doing anything to A. It's just the symbol to say that we had a matrix A and we're taking its inverse. Well, to find its inverse, you're going to take the main diagonal, AD, and we're going to switch those two numbers. We're going to take the other two numbers, C and B, and we're going to make them negative. And then in front of that matrix, as you notice, we've got a fraction 1 over A times D, so note the main diagonal, minus C times B. So 1 over the main diagonal multiplied minus sort of the other diagonal, right? That upward diagonal multiplied. We're going to get a fraction out in front. So let's try that once down below here. So we've got a square matrix, a 2 by 2 matrix. Right? In order to find an inverse, it does need to be a square matrix, but we're going to find that 2 by 2 matrix, or inverse matrix, by saying 1 over. And again, later we'll give this a name, this formula right here, but for now we're just going to say the main diagonal multiplied minus the upward diagonal multiplied. And basically for us, that just comes out to 7 minus 6 is 1, 1 over 1 would be 1, and really that fraction isn't doing anything, so we can sort of ignore it. That just turns to a 1. However, this is a great time to bring up the fact that not all matrices have an inverse matrix. What would have happened if, again, A times D minus C times B came out to 0? Again, 1 over 0 is undefined, so we wouldn't have an inverse matrix if that, again, number in the denominator comes out to 0. You can have inverse matrices matrices that don't have inverse matrices. So just keep that in mind. Then over here to the right, again, we got to actually construct our matrix. We're going to take our 1 and our 7, and they're going to switch spots. So again, down here, that'll be a 7 and that'll be a 1. And then over here, we're going to take our 3 and our 2, and we're going to make them negative. We're just going to attach a negative to both of those. So we're going to end up with a -3 and a -2. Realize you'll often get fractions or decimals in there. If this fraction out in front wasn't a nice clean 1, we would have distributed it to all 4 parts, right? That scalar multiple idea. So again, you'll often come out with inverse matrices that aren't pretty numbers. They'll be fractions, they'll be decimals. Now, that's great for a 2 by 2 matrix, but what do we do for other square matrices? If we want to find the inverse matrix of any square matrix, the easiest way to do that is basically take your square matrix, such as the 3 by 3 matrix we have right here, and we're going to attach it to an identity matrix. We're going to augment it with an identity matrix. So you'll notice I took my 3 by 3, I've got it right here in the first half of this very large 3 by 6 matrix, and notice we've augmented it, right? Right down the middle, we've augmented it with an identity matrix, basically saying that, again, to find the inverse of B, well, A times its own inverse, or B times its own inverse, should give us the identity. We've augmented the fact that we're solving for B, right, or solving for A, sorry, A will be its inverse. We're solving for A by augmenting it with I, solving for B, solving that system. Right? Just like when we had our coefficient matrix times our variable matrix previously attached to our constant matrix. Now, once we have this all set up, we've attached our matrix to an identity matrix. The key is we're just going to do RREF. We're going to find a reduced row echelon form. So we're going to turn this side of the matrix into an identity. It's going to be a 1, zeros, 0, 1, 0, 0, 0, 1. And the right half of our matrix will end up being our numbers. So again, we augment it. We basically do our REF, right? We find our REF for our matrix. We do Gauss-Jordan elimination, and we end up finding then our inverse matrix. So this portion, right, will be A inverse, right? That would be A inverse. So if this were A, if that were matrix A, we just found A inverse. Now, why would we do that? Well, to solve a system. It's actually a very, very slick way, a really fast way, almost as fast as our REF, probably just as fast, to solve a system. So here's what I'll expect to see on your page when you're solving a system. If it's a word problem, the first thing that we'll do is read through that word problem. Feel free to pause the video now if you want to and read through that problem. But what I'm going to do is take all that information and I'm going to construct a system out of it. So we know that all the money we added up, all the investment, is $500,000. The interest we earn on all three accounts, right, laid out here, is going to earn us $52,000 in interest. And then we also know that, again, the amount borrowed at 12%, which would be Z, is equal to 2.5 times what was borrowed at 9%, which would have been X. So Z equals 2.5X, right, will be our last equation. What I want to do with that then is construct a variable matrix, or essentially construct a system of matrices to describe that. So again, we've got our matrix equation that we want to identify, which is going to be right down, get it to show up here, just 1 second, right down here. We've got 1x, 1y, 1z, again, would have been equal to 500,000. We've got our interests, right, in row 2. And again, row by column, they would construct the left half of this matrix, the left half of these equations. But again, interest in row 2 equal to the interest. And then finally, I needed this equation, right, to have both variables on the same side. So we had to subtract 2.5x plus z would have been equal to 0. And so we've got that right there, which is where I got this equation down here at the bottom. The matrix on the left we'll call matrix A. Our variable matrix we'll call matrix X. And our constant matrix we'll call matrix B. Which means if I want to solve to find X, I just need to cancel A. Now you have to remember we can't divide matrices. But what we can do is multiply a matrix by its inverse. So show the inverse matrix, right, or show the inverse steps to solve would be our next thing to do. We've set up our system. We've constructed our matrix equation, right, or identified our matrix equation. Now we want to show the inverse steps to solve, which are right down here at the bottom. Again, I took what we already had, A times X. We multiplied by A inverse on the left side. Remember, the matrices aren't typically commutative. So since I multiplied by A inverse on the left, on the other side of the equation, I also need to multiply by A inverse on the left. It needs to be the first matrix on both sides of the equation. But remember, hey, if A is a 3 by 3, A inverse is a 3 by 3, then we should be able to multiply a 3 by 3 times a 3 by 1, right, matrix B. In that case, A inverse times A turns to the identity, and we just get X. A inverse times B will be our answer. Again, read back through that equation. It's a fairly quick set of equations, and it's the same set of equations every time. So it's a pretty easy thing to work with. Now, since we can let our calculators find that inverse, really that's all of the work. What I do want you to show me on the page, though, is what does that inverse look like, and then what are your answers? So again, the steps we need to show: identify the matrix equation right here, show those inverse steps right here, and then finally show the inverse matrix over here at the right. Note A inverse there. Let me get rid of that 0 in our way there. Okay, A inverse. Put that over just a little bit. But our inverse matrix is right here. And by taking A inverse times B, we get our 3 numbers there. which again are x, y, and z, are basically our three different interest formulas. Let's take a second just to see how to type, again, that inverse matrix, how to type that matrix in and get an inverse matrix on our calculator. Now, I'm just going to go see if maybe I've got one saved that's a square matrix, and I do. Down here, matrix D is actually a square matrix. So let's see what matrix D looks like here. Well, that won't work very well. That's an identity matrix. So let's edit that matrix. Let's go in here. And actually, let's just take a look at matrix C. Matrix C will work out for us. That's a 2 by 2 matrix. So if I wanted to find the inverse of matrix C, all I would need to do is say matrix C. So again, I'm going to go back to my matrices here. I'm going to pick matrix C, and I'm just going to attach a -1. Now notice we've been pressing second x to the -1. So let's just press that button. And again, there's that inverse symbol. C to the -1 is the inverse of C. And again, we can tap to the right to see those other numbers. It should be a 2 by 2 matrix. We can also say math arrow to fraction and probably get a much better looking inverse matrix. So take a second, grab your calculator, plug in matrix A, go ahead and find A inverse and make sure you get the same matrix we got over here at the right. Then try typing in A inverse times B and make sure that you get this matrix here. Again, this was matrix B, so A inverse times B should get you your answers there. If you have any questions, make sure you talk to your teacher. Otherwise, good luck. Hope you can solve those equations, solve those systems, and have fun.